Good afternoon, everybody.
Hi, Professor.
Good afternoon.
How are you today?
Good, good.
That's great. Today is our last class of the 42991. I'm very happy to finish this subject. Looks like everybody has very high marks for the assignment 1 and 2. Very great to see. Looks like everybody following well and understand, and then keep all our learning objectives. So very great to see your marks for the assignment 1 and 2. And today, we will first summarize what we have done so far for this subject and try to remind you. And at the end of the class, we will discuss about your question on assignment 3. Okay, let's start from just a short review of our Can you see the slide?
Yes.
Yes.
Right, that's good. So first, blank mode, we discussed about the socio-technical issue, how we can engage with our community and stakeholders to make sure all the necessary socio-technical obsession, also public obsession related to our difficult agenda. So drinking water from wastewater. So that's one of the issue we discuss about for your assignment. So we have a skill to make sure that how to engage, how to convince, how to inform. So there are several methods we have followed. Also, you have a great mark for the assignment 1. So that was the module 1. And module 2 was about the wastewater reuse plan. So we simply cover the wastewater design parameters, how we can utilize the different wastewater treatment plant, how the water treatment process working. So we cover very general principle and followed by detailed design of wastewater reuse and the membrane bioreactor. So we compared with the conventional wastewater treatment process with membrane bioreactors. So what's the difference? How we can compare in terms of cost and space and performance. So already you complete most of them, the module 2. So everybody got your assignment 2 marks, right?
No.
No. All right. Already we finished the marking, possibly today. Today, maybe we will send. So I think that most of people did a great job. And if you have any questions, so please contact me and contact Dr. Sharup Puncho. So we will double check and discuss about your marks. And that's we have finalized your assignment to now. Final module is about the seawater desalination plan. So based on scenario, so we get your basic information of the seawater quality, seawater capacity for desalination plan, so how we can design, how we can plan also. We like to look at all the water quality guideline, boron removal, also some of your brine management, also how we can shut down the plant and then reoperate. And that's our discussion point. So I'm sure that you already completed most of your assignment. So how to design your seawater desalination plant from intake, pre-treatment, and the reverse osmosis, post-treatment. So what's the design parameter? Also, we have used the software, which is WAVE program. So you have already familiar with this program, how this can make happen to complete your design of the reverse osmosis process. So that's all about the block 1 and block 2 and block 3. So I'm sure that you are very confident to design your wastewater and seawater desalination plant, including the community engagement. So that's very much necessary when you consider your plant design as well as the consultation. So I feel today that's our general information. Do you have any other question for your contents of the 42991 or assignment 3? So we can start to discuss what's your question for your subject. Any questions?
Yes, Professor, I do have.
Yeah.
So for the WAVE software, I'm a bit confused because when I put all the information, it's still giving me, when I press on the report, it's still giving me that there's something wrong and it cannot perform the calculations. I don't know why it's giving this error.
All right. Can you please share your just design so we can have a look
Yes,
together?
one second, please.
Please.
Can you see the screen?
Yes, I can see that. Okay.
This is the feed water.
Wow. Feed water and
This the reverse osmosis.
reverse osmosis. Okay. So just a second.
Okay.
Can you click the pass 1?
Sure.
43%. 1459. All right.
Should I press the summary report?
Yes, please. So this is based on your design, right? So did you utilize the example file which I gave you?
This one is, yes, modifications have been done to the file that you have set. But I also have another model. I've done another model from scratch. But this one is not giving any calculations. I have not tried getting the report for the first one.
I see. So which means, okay, your design is very, very large quantity of feed water, as well as your calculation of the pressure vessel and your maybe first pass, there is something is wrong. That's the reason why. Okay. Can you, which I gave you the file last time? Did I give you the file? Has to sit in water quality. Let me show you.
Professor, just to make sure that I'm right, the total number of elements, uh, is it calculated of the permeate flow times the recovery divided by the membrane area?
Yeah,
So it's the formula that's in the slides, am I right?
you're right. The problem is you design very big water quantity at the feed water, so that looks like it has a lot of error you can face from this software. So I like to reduce the little bit of your water quantity.
Professor,
Yeah,
can I add something?
yes, sure.
So I had this same problem as Olena when I first
Okay.
did mine, because the
Mhm.
feed water and the flux was running way too high for the
Yeah,
parameters.
yeah.
I ended up breaking it down into smaller feed flow into like 10,000 cubic meters per day, and then having more treatment trains to allow the calculation.
Mhm.
Is that something you agree with?
I think so. Can you, okay, let me just, can you show your feed water?
Hey, Professor.
Yeah, you failed converge. So review your design, because your design flow rate is not good. That's the reason why it looks like there is something is wrong with the design factor.
And also I have a question on
Mhm.
the pressure vessel and element calculation. I was wondering if you could give us an example, because every time I input the calculated pressure vessels from the formula, the wave program tells me that there's not enough elements, or the flow is too high, so I have to increase the elements um to make the program work.
Mhm. Okay, so let's finish first. First, Olina problem. Olina, I have sent you one file through this chat box. Can you see chat box? Let me
Yes,
finish the Olina one. Okay, can you download this file?
yes, I'm doing this now.
Okay, and then can you open the, yes, so please, can you open your file, this one? I think that looks like a little bit different from your design. So
Mhm.
let me, and then can you open this file from this, yeah, your software, in your software?
Okay, I'm doing this now.
Yes, please. So what I feel, your module pressure vessel is a little bit lower as well as element compared to, okay, this example. So that there is something is not flowing in your, so yes, you can, yeah, exit wave, yes.
Also, Professor, quick question. If the pH is 8.1, then we should add an acid to reduce the pH, right?
Right, that's correct.
Okay.
Okay, so you are now is opening the file, right?
Yes,
All right.
I don't think it's working.
And then can you download the file?
Yes, I did.
Yeah, download and then open it.
This is it. It's downloaded.
Mhm. Can you open it?
Yes, it worked.
Mhm.
I think.
Okay, so compared to your design, okay, can you click the summary report now? Not, okay, so it has to be, yeah, you have to wait. Okay, can you click the summary report?
Okay.
Yes. So this should works. And what's the difference from your design? Looks like you have a less element, less pressure vessel. So that, yeah, now it looks like okay, right? Can you go design only? Design can go down, go down, go down, go down, go down, yeah, go down. So you can see, yeah, go down. Yeah, right. Can you go up? Yes, go up, go up. Yes, you can see arrow design warnings.
Mhm.
None. It's that's exactly, when you have no warnings, which means this is the well designed. But can you click the reverse osmosis now?
Yeah.
So when I see your pass one, can you go pass one? So you can compare your pass one, pass two. So it used to be 1,400 something in your pressure vessel, right?
Yes.
Now you have 2,600, right?
Yeah.
So in fact, you designed the very less number of pressure vessel elements so that your water flow balance is not really well, so that this cannot be calculated in your report.
Mhm.
That's the reason why. Okay, you design very huge amount of feed water, and then you design less pressure vessel element, so that a lot of errors there, so that you cannot get any report. So you can start with this one.
Mhm.
Okay, you can reduce if you want to use your design, you should have reduced your overall your the feed water. So which means 2,600. You had 1,400, almost 2 times. You need less feed water to complete your design. Initial feed water. Do you understand me?
Yes.
So that you can make a little bit nice summary report.
Mhm.
Otherwise, yeah, current system, yeah, this is working well. And then this can be, I think, your starting point to design your process. And then also you can see the pass two. You can click the pass two. And you click pass two, yeah. So you can see the stage one, stage two. So how many pressure bus element do you incorporate? So that's the one of the most important factors. You can try to create the design owning or no design owning, because the flow rate, if it doesn't really balance well, you cannot see any summary report. So you can start from this report example, and then you can finalize your report assignment. Okay.
Okay, Professor. And do we need to add something for pH adjustment in first pass and second pass, or we can do just
Okay, so it depending on your summary report. Can you go summary report again?
Yeah.
And you will see the scaling potential in your report. So you have to see it carefully in your report, what information you can get. So I can show you. Can you go down? Yeah, you can see carefully, right? Can you go down? More, 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 more. Yes, here you can see arrows chemical adjustment. So when you have a red color means you have Onyx. If you see the arrow solubility Onyx, so Langella saturation index LSI value is more than 0, which means you have a positive value, which means this is the very strong inorganic staining potential. mostly calcium carbonate or calcium phosphate sulfate. So your PAS2 will have a very strong potential. That's why it shows the warning, right? And then anti-scalant may be required. Consult your anti-scalant manufacturer for dosing and maximum allowable system recovery in PAS2. So red color, so it shows your owning of the design for potential inorganic scaling. So based this information, so you go back to chemical, so you can reduce some more pH, and then you can add your anti-scalant, and then you can resolve this kind of potential of the inorganic scaling. So you are correct. So you have to put your chemical anti-scalant based on this report.
So the anti-scalant also affects.
Right, anti-scalant will affect in your PAS2. So you can go reverse osmosis. So can you click the feed water? Okay, first feed water. Can you click the feed water?
Here?
No, not this one. In the tab. Feed water arrow and summary report. So you can see, okay. So this is the initial your feed water. So initial feed water, let's say you assume that your pH is already 5.5.
Mm-hmm.
So it's coming through from your initial pH to RO is 5.5. So you change your pH from your receiving feed water. And then when you operate RO, because of you are concentrating your pure water and then your brine, right? So your brine is becoming more and more high pH, which means you will get the more fouling potential, right? So in this case, you can go to RO, reverse osmosis. So reverse osmosis, so here you can decide add chemical degas. So you can click the add chemical and degas. So you can decide pH, what's the pH you want to adjust at the PAS1, PAS2. Yep. And then you can also put the anti-scalant here because you have some fouling potential in your concentrate, right?
Mm-hmm.
So you can put the anti-scalant. So you can, depending on your design, so you can put maybe 1 to 3 milligram per liter range, and then you can reduce the overall the fouling potential. So you can also change the pH. You can reduce the pH more. Let's say pH 4. You can put the pH 4. So also you can have a less likely inorganic scaling potential, and then you can click OK. Right? So based on that, you will see also what's your response from the anti-scalant, hydrogen sulfate, and feed water. So that's how you can design your overall. Yep. Also, if you click the PAS2, and then you can also click. So your PAS1, PAS2 is different. So you can click the pH maybe less than 7 or 8, say 7 or 6. 6, let's put 6. Okay, 7 to, okay, put the 7. Your range is 7 to 12, and then click it. So you can see you will have a 7 because less pH will have less fouling potential of inorganic, so that you can have now put the summary report again. So you already respond your chemical, anti-scalant, and your pH adjustment. So you should have a much better summary report. So you will see how you can decide your summary report. So it disappear, right? Because
Yes.
we change pH, we add anti-scalant. So red color initially it was there. Now it completely disappear, which is you have designed very well for this fouling potential as well as all the water flow.
So Professor, just to make it more clear in my head, for this case, we had the pH less than 7. For the assignment 3, we have the pH 8.1. So we should decrease very much the pH, because after the RO, the pH will increase again very much. So we have to decrease it again in the assignment, right?
Okay, assignment, your final concentration of the pH should be like a
Around.
drinking water quality. So I think the neutral pH is 7.
Yeah.
So this is because initial pH of the seawater is 8. That's the 8 is very much easily hydroxide, and then easily you create the more inorganic scaling, so that we like to reduce the pH. So acidic pH has a better operating condition of your RO plant. But after RO, so our drinking water, we like to drink the neutral pH around 7, right?
Yes.
So we need to adjust the pH 7 in our post-treatment and drinking water. So that's how it works.
Okay. Thank you, Professor.
Thank you. Okay, next Sing, you want to have any
That's all for me.
question? Okay, thank you, Alina. Yeah.
Sorry, Professor, I can't really share my screen because I'm on a work computer. I don't have
All
Wave
right.
program, but my system is working. I just wanted to double check the element calculations with you.
Element calculation. What do you confirm with me?
So
Mhm.
do you have an example that we can look at just so we can go through? Because every time I input my calculation, Wave tells me that I have to increase it to make the design work.
Okay, let's just show our class note. Let me show you. Okay, can you see the slide?
Yep.
Do you remember that we discussed about 10 steps? 10 steps shows how you calculate. Okay, element, you want to calculate element. Okay, this is the example. Do you remember this one?
Yeah, that's what I've used.
Yeah,
So the total
Yeah.
number of elements.
yeah.
So is the feed water the 720 meters cubed per day?
Yeah, yeah.
Is the permeate flow from Wave?
That's the permeate. So it has to be, your feed flow should be like you are using 75% recovery. So it has to be almost more than, you can divide by 0.75, so that you will get almost 1,000 something, right? 1,000 something cubic meter per day. Feed water, you have to decide. So let's say you have 1,000 cubic meter per day feed water, 75% recovery means 750 cubic meter per day. Am I right?
Yeah, yeah. So where do you get the feed permeate flow? Is that the one? Is that the value given by Wave?
Okay, value given by yourself. So when you see our scenario, in fact, we ask you to design your seawater desalination plant 250,000 cubic meter per day. That's
Yeah.
what we decide. But you know, the design, you don't have to design one plant only, just a small, let's say you design 10,000 cubic meter per day, multiply by 300, you can have a 10,000, so multiply by 35, which means you will design 250,000 cubic meter per day. So you design 10,000 cubic meter per day, and then you can multiply by 25. 25 your design train, and you will get 250,000 cubic meter per day.
Yes,
So,
yes.
yeah. So that's you can reduce the volume, but some student, I show the example in this, let me show you this one. In this system, just for example, where is, okay. So this one, okay, if you see here, so you can put your product water in this system, 250,000 cubic meter per day. So this feed water will be automatically calculated based on your recovery here. So 44%. Yep. And then you have a pass to your 85%. So based on this two recovery ratio, you will get this feed water, the volume of your capacity. So you can put the feed water first and then give your overall your recovery, and then you will get the product water different value, but you can be similar. It doesn't have to be exactly same as 200,000 cubic meter per day. So you can decide based on your feed water or product water and recovery. So that's the three parameters you can consider.
Yep. I've broken down into 25 something trains to make the calculation to reduce the power consumption as well.
Mhm.
And then I just wanted to confirm the other parameters as well. The LMH flux, where do we get
Yeah.
that from?
All right, LMH, okay, based on slide.
Is that
Yeah.
always 25 as in by default?
Okay, this one,
Yes.
I think, okay, this is given by the manufacturer because some membrane has a very high flux. So they may have a little bit more like 40 LMH, but mostly our membrane, high rejection of the salt, average flux, we calculate 25 LMH. So you can calculate as a 25, that's fine.
Yep.
I have one question there, if I can.
But okay, okay, let's say,
Sorry.
let me stop here. If you look at your RO software, yeah. So let's say flux, 18 LMH, because you design automatically. This is not given value. This is the general your information for rough calculation. But when you put your value, so they will automatically calculate 18 LMH, which is the very good range of your average flux.
Yeah.
So that you can utilize as needed. Also, if you see even brackish water, also they have LMH, 18
so you
LMH.
can use the wave value as well.
Yes, it doesn't have to be
Sorry,
fixed.
one quick question.
Yeah.
So I was working this morning. I was going through the technical data sheet from DuPont. And for the membrane I'm selecting, I'm getting an LMH of 8.5. So is that weird in this context?
Okay, 8.8 LMH for average flux, right?
I'm using the 4. I'm trying to compare using the 400 and the 440. Yeah.
For just a second, which one you are talking about? Just a second.
I'm
using
the 8-inch 400.
Okay, you are using 8-inch 400. So which means this one? Is it this one?
HRL, just give me 1 second. Taking a look at it right now. Opening my file.
Yeah. So for example, if we change from SW30XH44I and then we change this one, let's say, okay,
Yeah.
what's the change of the flux? Because it was 18 LMH. Now we select more, higher flux membrane.
Yeah.
That's the reason why it's automatically whatever you select, depending on our pressure, depending on our recovery, this will automatically calculate. So you can change because whatever you change, what will happen is that you will get the different water quality.
Yeah. But for
So
example,
yeah.
if we use the technical data sheet to calculate, to have a quick approximation of how many elements we need. For example, if I use the technical data sheet for the 400, it says that I'm needing around 33,000 elements.
Yeah.
And if I use 8 elements per vessel, I'm getting 4,000 vessels. And yes, but yeah, my flux, I took it from the technical data sheet, but it's 8.5 liter LMH.
Okay. So have you ever clicked the summary report? What the summary report, do you get any error?
I'm still trying to fix that around it because I'm using the parallel desktop in my Mac and it's getting a lot of power from my computer.
Okay.
Yeah.
Okay, that's fine. Even though it's LMH, doesn't matter because just the matter of you have less flux, then this will impact overall your water quality as well as your recovery, some of the fouling potential because of your very low flux compared to others. So in this case, yeah, you have to look at carefully because you are still, okay, when you see this one, okay, if you have no design on it, that's fine. All right. Also, if you have no fouling potential, that's fine. Yep, even though you selected a little bit of less flux, but less flux means you will have a very high rejection. High also some of your different flow rate data. So in this case, as long as you don't have much fouling potential, much design on it, that's fine. But if you feel like, okay, if you see the chat box, I linked the one example file. So you can just utilize this one as a starting point, then compare to your result, how this can change. And then you can see how this can be varied and then how you can make a better design. So this will show from, okay, when you see this value in your summary report, maybe if you can see, okay, your energy consumption overall, when you design such parameters, we will get around 7 point, what's the 7 point energy? Let's say energy consumption. So you can see energy, okay, let's specify energy consumption. Yep, 5.57, 0.91. So when you design your membrane and your element, and you found out, okay, this design has the lowest water energy consumption, yeah, you have done very great job for your design. Otherwise, yeah, you can follow this example and then see all the different parameters and how you can change, your element flux and all the different your energy consumption. So that's what I want to see from your assignment. Also design only, yeah, make sure that as low as possible, not too many design running. So you can utilize your design almost zero owning system. Okay, Maria?
Got it. Thank you.
All right, thanks. Okay, sorry, Xinghao, you
Yeah.
have
Yeah,
you can
sorry.
continue.
Yeah, wasn't done yet. Just the other parameter, the flow.
Flow, yeah.
Where do we get that from the manufacturer spec?
You mean the flux RMH?
Not the LMH, the other one. Can you minimize the wave window, please?
Wave, okay, yeah.
Yeah, so the 41.6 cube per day, that value.
Okay.
That's
one
yeah,
is
sorry, I was
the
just taken straight from the manufacturer sheet.
okay. This is I think
That's to convert.
unique conversion. This is a unique conversion from you have a RMH, and we want to utilize as a conversion matching like a cubic meter per day. So it's RMH we convert to cubic meter per day. So you can remove all of them, and finally you got the 35.
In the manufacturer spec, it's given in meters cube per day.
Manufacturers, which one?
So I mean the 41.6 cube per day.
Okay.
That's taken from the membrane specification, correct?
You are right. This is from here. 20 RM, 25 RMH. It's a unique conversion. So RMH, you want to convert to cubic meter per day. So you need the 41 LH will be equivalent to cubic meter per day. Do you understand me? Because 1 cubic meter is 1,000 liter.
Yeah.
1 day is 25 hours. That's the reason why you get 41.67. Your number.
Does that come? Oh, did you so the 41.67 is derived
This
from
is
the 25
only
LMH.
for only for this is not relevant to any of the. This is only unique conversion.
Right.
Unique
Okay.
conversion,
yeah.
Okay. Anything else? How about other students? No more questions?
I was just the plant shutdown and operation section. I remember emailing you about that. I couldn't really find any I'm just not sure how to make the layout for that one because I've never really seen a plant shutdown and restart plan before.
Okay. Because why we have to shut down is the desalination plant, which are expensive, very energy intensive process. So that when we have a lot of dam water, like Warragamba Dam is full, so that we don't have to operate desalination plant, which will save a lot of energy, so that we can stop. When you have a very heavy rainfall and then our dam level is full, so we shut down. Of course, this is not common practice, very special practice, but when you have a drought, the dam level decreased almost 50%, less than 50%. So in this case, we start our plant operation. So in this question, you don't have to mention about how you shut down the process, how you start reoperate your process. So what I am asking is that how much dam level rise, and then what's the desalination plant has to be shut down. And then when your dam level decreased, how you can reoperate your process. So restarting plan as well as depending on the dam level. So it shows in the some of my. Did I send the link to you? You remember I gave you some link for shutdown planning and then desalination starting planning, right?
Yeah, so that's in the Sydney water fact sheet you sent me.
Right, you're right. That's true. That you can utilize as a summary. And what's the most important from July this year? I think that almost 1 month later, the Sydney desalination plant has decided to continue to operate the desalination plant
Yep.
without any shutdown. So you can mention at the last sentence, but now this is no longer existing for shutdown and reoperating planning. Now is the Sydney desalination plant from July 2023. We will continuously operate our desalination plant.
Just at a reduced output, right?
Right. Also, we can say this is the one of the response of the climate change.
Yep.
So that's the perfect. You can get your answer.
So it's like an
in your
overall
report.
overview, right? Overview
Exactly,
of like how
exactly,
you
exactly.
why we do. Okay, it's not like a
Right, you're right.
specific like
No,
step
no,
by
no.
step.
I don't. I'm not
Oh,
asking you.
okay.
I'm not asking you to have a one by one shut down the switch and then change
That's
the
what I was thinking.
membrane. And that's the exactly you are misunderstanding this question. So I don't. If you like, you can do it. That's the another level of the professional report. You will get the better marks if you can. Yeah, because absolutely that's the another level of the skills. But what
Yeah.
I'm asking is very simple. Love way of why we need to shut down. Why we need the real prayer now is completely we will operate fully.
Yep.
You
Yep.
understand,
Thank
right?
you. Yep.
Yeah,
Yep. Perfect.
yeah.
Thank you.
Okay. All right. So almost we finished this class today. So if you have any questions still, we have several days more before deadline of your assignment. So please send the email. I will respond to you. And then hopefully you can finalize your assignments and then have a confidence of your design of water and wastewater treatment plants. And then if you have any other issues or any other further study of your design or some water advanced treatment process, please let me know. We can keep in touch and we can also learn more together in the future. Thank you for your help for last 6 months. I'm very great to work with you for this subject for 2991. I wish you all the best for your subject and assignment, and then have a great winter break. Thank you.
Thank you, Professor.
Thank you very
Also,
much.
yeah. Also, if you all agree, yeah, I like to just a second. Let me share. Let me stop this one.